Okay, so here we are where we left off yesterday, and we have copper and silver reacting. As you can see in panel A, copper is that metal, it's copper colored, and we have a colorless solution inside the test tube, and that solution has silver nitrate in it. When in panel B, the copper is submerged in the silver, a reaction automatically begins. It is an oxidation reduction because copper is going to go from a 0 oxidation state to a +2 oxidation state, and silver is going to go from +1 to 0. And so we're actually plating silver and we're dissolving the copper. And so we'll see silver develop in the very bottom of the test tube, and the copper becomes copper nitrate in this case, and we get that blue color. The nitrate is what we call a spectator ion. You don't see it in the equation because nothing happens to it, nothing changes. It's there just to keep the solution neutral in terms of charge. So what if the electrons were forced to pass through an external wire is the question here, and we would actually see some charge being transferred, and it would be working as a battery. So it could light up a light, it would make a voltmeter go to a positive voltage. So galvanic cells or voltaic cells, these are basically batteries, and these are a spontaneous reaction, and that means that delta G would be negative, and it would happen without any interference from an outside source. So it's designed to take advantage of the movement of electrons, which occurs during an oxidation reduction reaction. So the half reactions in a voltaic cell are separated into two compartments or two half cells. And so we would have a beaker on one side with one solution, we'd have a beaker on the other side with a second solution. We would have to then connect those two so that we could keep charge being neutral, because electrons would leave from one side and enter the other side. So we need something else to balance out the movement of those electrons. So oxidation at one electrode, the anode, and the way I remember where the anode is that oxidation and anode both start with A, and then reduction and cathode both start with a consonant. So oxidation and anode with a vowel, reduction and cathode with a consonant. Electrons move through the external wire from the anode to the cathode. It goes in alphabetical order. These moving electrons can be used as a short source for electrical energy, or they are a battery. So oxidation reaction occurs in one cell, and the reduction reaction occurs at a separate cell at separate electrodes. So we'll need two electrodes, an anode and a cathode, and we will have two compartments. And the anions flow to the anode, and the cations flow to the cathode. So here's our setup. This is the same thing you saw in that first reaction. On the left, we have a solution of copper 2 nitrate. We have a copper electrode, and so whenever you have a metal in solution, you match the anode to that metal if it's at all possible. In the right compartment, or the right beaker, we have silver nitrate solution with a silver electrode. You'll notice there's a U tube in the center, and I don't mean YOU, but U-shaped tube that's inverted here that has salt in it. It has, in this case, sodium nitrate, and this bridge allows the anions to go to this side, to the anode, and the cations to flow to the cathode side, so that we can keep the electrical neutrality of both solutions. So the electrons here, copper is going from Cu0 to Cu2+, so it's losing 2 electrons, and those electrons are flowing up through the anode through the wire, through the voltmeter, back down through the wire and into the silver cathode, which then those electrons will attach to a silver ion to make silver metal. So the copper electrode will actually decrease in mass because it's going from the solid to the aqueous or charged state. And so copper is leaving the electrode to go into solution. And the anode, or the cathode, the silver electrode, will actually gain mass. It'll get heavier because silver atoms are depositing or coating that electrode, making it heavier. So, and this is going to summarize what I've just said. Copper metal anode dips into a solution of copper 2 ions. Silver is in a solution of silver ions. External wires are connected to a voltmeter, and that's just so we can measure how much current is flowing. At the copper electrode, the anode, the electrons are produced, and they are generated here, and they go through the wire, and they flow from the anode to the cathode. And it's indicated how much potential or what the cell potential is here at the voltmeter. The electrons enter the copper or the silver cathode, and at which time they would encounter a silver ion, and it would create silver atoms that would deposit onto the electrode. So as the oxidation occurs, the surplus of positive ions builds up at the anode. And so when we're generating positive charge, let me go back. When we're generating positive charge here in this beaker, those negative ions have to flow in to make it electrically neutral to neutralize the charge that's building up. And the area near the cathode becomes deficient in positive charge because we're taking silver ions out of solution and making silver metal. And so the salt bridge would give us the ions to balance that out. And so if I'm losing positive charge in the cathode region, then my positive ions would flow into the cathode beaker. So the salt bridge is a porous material consisting of a concentrated salt solution. It's typically sodium or potassium nitrate because both of those are very soluble. Anions flow toward the anode and cations flow towards the cathode to replace the charges that are being consumed or built up in those two regions. This flow of ions from our salt enables the electrical neutrality to be maintained, and so the circuit's complete and the current is allowed to flow. So here's the salt bridge again. We see that our anions are flowing into the anode beaker. Our cations are flowing into the cation beaker. Cell notation. This describes in kind of a shorthand notation what is happening inside that cell. And we always do oxidation on the left and reductions on the right. And so we go from a single vertical line will separate things that are in different phases, a metal or aqueous versus a metal versus an aqueous solution, or metal versus liquid, or liquid versus gas. Any two phases are separated by a solid line. A double line indicates that that is where the salt bridge is. And so the salt bridge is between the copper solution and the silver solution. We do not include any spectator ions, and if it is at 1 molar, which is standard cell concentration, we typically don't include that it is at 1 molar. The only time we typically include concentrations if it is not at 1 molar. So, galvanic cell summary. When we put them into two different compartments, the oxidation reduction half reactions, the half reactions are occurring in each cell or half cell. and it enables the spontaneous redox reaction to occur and generate a positive or an electrical current. In one half cell, the anode oxidation is occurring. In the other half cell, the cathode or the reduction is occurring. Each half cell consists of an electrode dipped in a solution, an aqueous solution. Half cells are joined by an external wire that allows the electron movement to pass through the voltmeter, and the salt bridge is allowing for the ions to move to maintain electrical neutrality. If you're generating a positive charge, anions have to flow in. If you're generating a negative charge, cations have to flow in. So we will pick up here on our next lesson. Thanks for listening. Have a good day.